Have you seen this ad? I thought it was pretty cool, and it plays on this company's website, right behind the words, "The strongest, most durable welding tables ever made." But this got me thinking, why does this table company get to make this claim? I know many other table companies, like WeldCell, BuildPro, Blueco, Certiflat, Langmuir, and none of them say this. Is there some official standard that I don't know about? Or is this just a bold marketing claim? What makes a welding table the strongest and most durable? Can any company just slap that label on and call it the best? Or does dropping a car on it really prove it? Or did they have to pass a series of tests? Well, today I'm digging deep into these claims, and trust me, you're going to want to see what we find. Just so that I was clear on what this really means, the definition of the strongest refers to having the power to move heavy weights, or take on physically demanding tasks, or be able to withstand great force or pressure. And most durable means able to withstand wear, pressure, or damage. This company claims to be the best in both categories. That's a massive claim. But there's one thing, anyone can make these bold statements. So let's put their tables to the test and see if they really live up to the hype or if it's just all talk. I would like to see how the strongest and most durable table actually performs in action. But how can I know if these tables outperform all the other ones in strength and durability? Well, a couple years ago, I reviewed a bunch of great welding tables. Having the opportunity to use every single fixture table gave me the inspiration to build and design my own. Like the WeldCell, made from cast iron. You know, the ones that last for over 100 years? Or seeing the massive amount of ribbing underneath the Certiflat table. And even liking the telescoping legs on the BuildPro. So I took the best features from the best tables and designed my own, the Fireball Dragon Wagon. I want to compare the Siegmund table against the Dragon Wagon and see if they can keep these claims. This type of table is popular, and it's small, but I think it's okay. Small tables generally are lighter in construction, which in turn requires better design to keep its strength, where big tables can supplement poor design with just sheer mass. So, in one corner, we have the Siegmund table, weighing in at 425 pounds, measuring 1200 by 800 millimeters, and costing $3,266. And in the other corner is the Fireball Dragon Wagon, weighing in at 553 pounds, measuring 54 by 30 inches, and costing $3,000. The Siegmund table is built from many pieces of bar stock and plate. The top, the sides, and the ribbing are all separate pieces. Then the tables are joined together by welding the intersecting seams, and tacking the ribbing underneath to help prevent distortion. From there, the table goes to the milling machine, where the table gets its holes and removes any excess welds, and flattening the surface. From there, the steel goes into a big oven, receiving its heat treatment. This makes the table very hard, but the trade-off is that the table may not be as flat as it was, due to the high temperatures. And since the table is hard, it can't be remachined, or it will lose its new surface. On the other hand is the Dragon Wagon, made from strong cast iron. The benefit of cast iron is that it allows me to create complex shapes into a single seamless piece. Once I have my desired shape or pattern, it gets put into a large box and filled with sand, creating a negative space. A lid goes on, and molten metal is poured into the box. Once the molten metal has cooled, the box is then broken apart, revealing its final shape of the table. The table is rough and oversized, and is now ready for machining. Here's where it gets its holes and is flattened. From there it goes into the dip, turning the cast iron into dragon scale. Now knowing how the tables are constructed, I want to run the Siegmund table through a series of tests to see if they can truly claim that they have the strongest and most durable welding tables. Let's break it down. I want to see how they handle the various hazards they will be facing in the real world, like weld spatter. Then we'll test its overall construction, how well it can handle heavy loads, and how strong the sidewall is. Then we'll look at what's keeping it off the ground. I want to see how the leg connections hold up to any shop accidents. So let's get started. The Siegmund table has a plasma nitride surface, and the Fireball has dragon scale cast iron. So to test their surfaces to the extreme, I'm going to simulate years of abuse. I'm going to set my welder to its poorest settings, generating the most spatter possible, and run a bead across a test bar that will be sitting on top of these tables. Then afterward, I'll clean up the surfaces and see which table handled this spatter the best. Before we can proceed, we want to remove anything that's on the surface of each table. Now we slide the tables together to make this test fair. This is a nitride coated and this is dragon scale. So I want to have a disclaimer. If you're going to be welding on your table, you probably should be using anti-spatter spray. The next thing, have the welder setting correctly. That way you reduce the spatter. I purposely have all of these conditions incorrect. That way we get the best torture results possible. Remember, this is a torture test and we want each table to be tortured the same. What I mean by that is if I start welding on this bar at this end and I start going over to here, well, eventually some of this spatter is gonna spill over onto the Siegmund table. So that's not fair to take some of the brunt of the load of the spatter. So what I think I'm gonna do is I'm just gonna go from this edge to the center and then from that edge to the center. We're gonna split it. That way the spillover is equal on each table. So let's see which one wins the spatter test. Okay, 3, 2, 1, go. Oh man, this machine set so wrong. This is the most ugliest weld I've ever seen. You can see BBs rolling everywhere. Woo! Oh my gosh, that looks a mess. Okay, before we get too crazy, let's go to the other side. 3, 2, 1, go. It's interesting, I don't see the spatter rolling. It's just hitting the table and stopping. It's some serious punishment for this table. Woo! Wow, look at those results. That is a hideous weld. Okay, this is absolutely brutal. A couple things that I'm noticing is that I got off just by a skosh on my weld, so we're down to maybe a 1/2 of an inch lower from my previous test over here. Is that gonna make that big of a difference? Probably not, but it's still pretty close. The other thing I'm noticing is how far out the spatter is on the Fireball versus the Siegmund. The spatter is really close to the flat bar. Now we haven't wiped anything off, I'm just doing some observations here. If you look at the streak, see how far it traveled and then it stopped? I don't think it stuck, so let me just touch it. Nope, see, it's just there. It's not even on the surface. Take a look at the Siegmund table. I don't see a lot of streaks here. They all look like they just landed and stuck. And as you can tell, I'm trying to move one up. It did come off, okay, but they didn't go very far. The smaller ones seem like they didn't stick that well. All right, let's get the bar off. Ugh. Let's start over here with the Siegmund table. Let's just do a hand wipe test. Not a lot's coming off. Actually, nothing's coming off. That is all stuck. Oh, some of it's coming off. I pushed really hard. This is cool to the touch, by the way. Let's do the Fireball Dragon scale here. We got a couple stragglers that landed on there. This is a tough test. It's interesting how they kind of like stick around the rim right there, right where that chamfer is. Overall, hands down, Fireball has way less spatter stuck to it. Let's use the scraper. This is the appropriate tool for removing spatter on a fixture table. It's designed to scrape the table without damaging the surface. The 45 cuts the chamfer. The straight edge cuts the bore if there's a BB stuck inside. It's heavy, so that it just plows right through the spatter. So let's plow it off. Because there's cast iron underneath, it just pops loose, just like it regular does. There's spatter inside the hole, this tool pops it off. See, pop.
Nice.
Pop, just like that. It gets it out of there, cleans it. There's a nice big fat one in there. Boy, that looked pretty scary, but overall, not too bad at all. Okay, let's do the Siegmund. Okay, it's coming up. Overall though, that also did a pretty decent job. There was still a lot more stuck on there. Okay, let's do a Scotch-Brite test to see how clean it can get afterwards. Is this just cosmetic or is this permanently damaged? The spatter marks on the Siegmund table are very visible, clearly visible. Can't really feel them with your fingers, but they are there. Invisibly they're there. It did pretty good. And then the Dragon scale did a much better job. You got some speckled spots, but I can't feel them with my fingernail. But overall, I think the Dragon scale did a better job of hiding that tortured mess. I don't know, I'll let you guys decide which table did better. These are one of the reasons why you're buying a premium table. They're designed to take abuse. Well, that was fun. Let's go to round 2. Fixture tables could face heavy loads on top of them over the course of their lives, but they still need to remain flat since we rely on their flatness as we build off of them. Typically, premium fixture tables have a ribbing underneath to keep the table strong and durable under heavy loads and remain flat. So I'm gonna put these two premium fixture tables to the test. One has two cross braces underneath, and the other has a vast interconnected webbing. I have an idea to simulate this. In order to make sure each design sees the same amount of load, they can just push off of each other. I can achieve this with just a simple hydraulic cylinder, with a load cell in between. In order to do this, we're going to tie the tables together at the top and have each one face to face. This will allow me to see how each table design handles this side by side, as I slowly increase the load, and see how well the table ribbing handles it. Then I'll assess how flat they are under this simulated load. Now, I'm going to walk you through how the rig is set up. Each table is bolted to the Fireball table with 4 bolts, so everything's torqued down pretty tight. Now, if you notice, this design and this design of this table are a little different. We have lots of ribs on the Fireball, and I only see 2 on the steel table. So what we've done is moved the pressure point that we're going to push a little bit lower on the Dragon Wagon. We are going to be pushing with this 8-ton hydraulic cylinder. The cylinder will put pressure right in the center of the tables. Well, at least on the steel table, because it's much smaller. We have also tied the tops of the tables together with this flat bar. These babies are going to be in tension. So these tables are coupled together, and then this cylinder is going to try to push them apart. And when that happens, we should see some deflection in the middle. And we're going to measure it with this straight edge with 3 points. One at the bottom, one in the middle, and one at the top. And we're going to slide some shims right in here between this point and the level to see how much bowing we're getting. Before I'd started any of these tests, I measured the flatness of these tables after dialing them in, the best I could. The Siegmund table was crowned 5/1000ths of an inch in the center, and the Dragon Wagon was dished by only 2/1000ths of an inch. The other thing to notice is that these two tables are not sitting perpendicular to the table right away. Before starting both tests, I checked the tables to see how square they were. The sidewall of the Siegmund table is out 35/1000ths of an inch over 2 feet. Causing it to lean a little backward. But the Dragon Wagon is much closer to being perpendicular to the surface, measuring only 10/1000ths of an inch out of squareness, causing it to lean slightly back. Anything can happen. We're going to stand way back, and I'm going to air actuate the cylinder with this hose that I'm going to be standing 20 feet away, because just in case something likes to blow, I don't want to be here to witness it. Okay, so a little scary, everybody's on edge, but this is what we got to do to see the results of how much deflection these two tables can take. 3, 2, 1, go. Ooh, going up fast. Ooh, okay, 300. Let's see where we measure. That's 600 pounds. Oh, I see very little deflection. I don't see any deflection on the Dragon Wagon, and I don't see anything on the Siegmund. So 0, 0. Let's crank it up and simulate dropping a car on these tables. Oh, 2 pumps are at 850 kilograms. All right, let's go just a pump or 2 more. Whoa, that went up a lot. 1,400 kilograms. Goodness, that's a car on top of these tables at the moment. Let's use a little bit more precision straight edge. Apparently it's gonna be down to the thou. About 25/1000ths or so deflection. Maybe a little more, 25, 26. Okay, they're neck and neck. 25, 26/1000ths. Go where? Keep going. We go up just a little bump more. Okay, here we go. Whee! That's another 500 pounds. Oy! 1,800 kilograms. I'm nervous. One more. 2,000? 2,000 kilograms, that's 4,000 pounds. 19? Oh, that was 2 clicks. That went way too high. 2,317 kilograms. Holy smokes. 5,108 pounds, those tables. There's that much weight on them right now. How long is my rope? I go way back here. I can't even read the meter anymore. Oh, I'm hearing something. Something's moving. Something's moving. 5,000 kilograms. This is freaking scary. Overload. Meter stopped at 6,000 kilograms. 13,222 pounds sitting on those tables. Holy smokes. Whoa, I want to get in there and measure them, but I'm scared as all get out. Okay, I'm gonna have to do it. I can see the tables bending. There's a definite curve to them. I don't know if I want to get up to it. I didn't think this part out. How about this? I don't want to get up there and fiddle around with it because I'm scared. I'm gonna get up there, I'm gonna release the pressure really fast, and then we're gonna measure it to see did they stay, because I think that's almost more important. Who cares that they deflected? Yeah, there's 13,000 pounds on them, right? Big deal. But do they come back flat again? That is the most important part, okay? So let's test that part. Oh, look at them moving. Coming down. I'm sweating like crazy. My glasses are all fogged up. Wow, that was nuts. Let's measure the steel table first. So I can get a 5,000th shim down here on the bottom. So it still has a crown in it. Moment of truth. The Dragon Wagon. Did it come back straight? Oh, no, it didn't. Look at that. Okay, so there's roughly 10 thousandths in there. So they're both not flat, technically. Just one's crowned out and one's dished. That's impressive. But overall, I mean, that didn't wreck the tables. That's pretty good. Both these tables performed pretty dang good, within plus or minus a couple thousandths of each other. I'm gonna actually call it a draw, because I think they're pretty equal. And let's go to round 3 to see this next test. Since these tables are already bolted down and parallel to one another, instead of pushing off, what happens if we pull them together? This simulates using the table as a surface to build sideways off of. After all, as a designer, it's important to make sure I've designed my table in a robust way to support any kind of load, even when forces are pulling against the sides. So here's how I think the test should go. To keep it fair, we should pull equally against each other. So we'll attach a come-along to each table, and then pull to recreate a simulated load, testing the strength of the sidewall of the table. Now, what's gonna happen is I'm gonna put this come-along, and when I hook it into the eyelet, it's gonna pull on this load cell that's been bolted to each side. And then we're gonna take a measurement reading with the load cell and see with maybe 250 kilograms, that's 500 pounds or so, we're gonna watch to see which table design is handling the load the best. The other thing to notice is that these two tables are not sitting perpendicular to the table right away. Here's what I mean by that. Here's my Starrett 2-foot square. And just by bolting the table down, the Siegmund is about a 35 thousandths of an inch leaned back in 2 feet. And then over the entire distance, we're at like 150 thousandths or so with the level. So if this was me and I was gonna use this platen in this configuration, I would have to come back through with some shims and shim underneath this back flange over here to get it perfect. But what we're gonna do is we're just gonna give this a handicap and we're gonna add these shims to the measurement as we go, okay? So it's unfortunate that you have to shim this table up. It's supposed to be a machined surface. Machined surface should be a little closer than that, but what can you do? Doing the same test on the Dragon Wagon with the same square over here, we are much, much, much closer. And it looks like we're about 10 thousandths of an inch in 2 feet. I wouldn't worry about shimming this. If I was gonna use this platen in this configuration, I would just build off of it and go. So I'm gonna call the Fireball good. A couple things to note. The Dragon Wagon is much taller, so we've lowered the probe height to be equal to the steel table. That way there's no mechanical advantage when the steel table is pulling the Dragon Wagon over. The next thing to note is I have no idea if these tables are moving, so I'm gonna leave the level here so I can physically look at the bubble and see the tables move. And I'm gonna be watching the load cell, and we're gonna be putting these two pieces of information together, see what's actually happening, and you guys can follow along and see what happens. We got some cameras lined up, so I'm ready to start pulling on this come along, get these two surfaces to come together. All right, let's start pulling. 5 kilograms, this is the chain load, 7, 18. Oh, I can already see something moving, they're already getting tight. There's 250 kilograms, so that's about 500 pounds of load. Okay, we got about close to the line here, and about 35 thousandths deflection. And then we're about the same on this guy. If not, maybe just a skosh better on the Fireball, but pretty close. All right, so let's keep going. Whoops, the other way. Getting close. Okay, 501. All right, we're at 500 kilograms. That's about 1,000 pounds. That's about where I would expect it to be. I don't think anybody's gonna hang any more than 1,000 pounds off these tables. Plus its handicap, we are 310 thousandths. Let's see, for the Dragon Wagon, looks like 160. So 500 kilograms is 1,100 pounds hanging off of this surface, and it's deflected 160. That's a lot, but it's outperforming this design 2 to 1. This one's deflecting a lot more, which doesn't surprise me because the designs are completely different. We're gonna add another 1,000 kilograms. But what I want to see more than anything is where the table returns. That is almost just as important on how much load it can take. Let's say you did need to support the load off it. Did we wreck the table or does it come back? How much elasticity do we have here? Ready? Here we go. I don't know if the chain fall is gonna do this. Might have to get a stronger chain hoist. This is only 1 ton. Okay, we're gonna max it out. We're gonna go. What was that? Pow! Something breaking. Oh, tacks broke. Never mind, we ain't going anymore. Let me look around inside here to see what tacks started to pop loose. It's kind of hard to see because everything's black, but yeah, I think that's where it's at. It started to pop right here on this gusset. Okay, one side tack popped loose. Let's just make sure that wasn't the Dragon Wagon. Because this is cast iron, if it made that loud of a noise, we would definitely see it. But I'm not seeing anything in here that signals that we have a crack. But now what I want to see is, did the tables go back to 0? So let's release all the pressure and then measure one more time. Okay. It's about the same. Came back to where it started from. Let's check this one. Yep, the Dragon Wagon came exactly back to where it was. So that was an unexpected result. I'm trying to test deflection, which table has more movement, and I wasn't expecting to start popping tacks on the back of this table. So in the line of safety for myself, the crew, and the table itself, I'm gonna call this round done. I love design science, and I find this fascinating. I learn more with failures to be a better designer. As a designer, I have to build tools to withstand worst case scenarios, like accidents. So I need to make sure the table and its legs are prepared for the worst. As an example, what happens if a table is moving along a shop floor and hits a transition or a hole and comes to a hard stop? Or even transporting down a stair step, or being backed into by a forklift. These scenarios aren't ideal, but they do happen. This leg is like a long lever. With so much of the weight on top, any sudden stop could put a lot of load on the leg to table connection. So I need to investigate these table designs further to create a test that replicates these scenarios. What I'd like to do is take this table and do a little more investigating on it and see how it's actually constructed, along with the Dragon Wagon. Okay, success. Get this cleaned up and see what we got. So we have our corners of our tables cut off, and I'd like to show you how they're assembled. But in blue here is where they beveled it. I don't know if this is the exact size of the bevel, but this is just for demonstration. All right, so the Siegmund table is a bunch of plate steel that's been welded together. We have a butt joint that goes into the corner, a leg mount with 2 small bevels on it that gets faced in the corner like this, and on top, this is the top surface with all the holes in it, right? All the holes, those are my messy holes. And it has a bevel on it, and it gets set down like that. So they have a small bead that goes here. They got a bead that goes up the sidewall here, down this other side. And then once that's all welded together, flip it over. And then the bottom looks like that. That's all that's holding that piece on, is just those 2 sides. Get out of there, fly. So now let's take a look at the real thing and let me show you how much weld they put in all these areas. So here's what we got. We got our leg mount here, we got our top, and then our sides. And then right here where I've etched, I didn't do that great a job of etching. Looks like we have a very small weld right there. A lot of joint left unwelded. And across the bottom, this is probably the biggest one. You can see the change in color there on the bottom joint where the leg mounts. Top to side weld is very small, very minimal. And then here's the side plate weld. And that's how this is assembled. Drawback that I have with this design by putting that floor in the corner is that it's really hard to access these holes in the top. These 4 holes are virtually impossible to get a bolt in there and tighten it up and put a nut on the bottom because of this floor right here. So what I've decided to do on the Fireball table is to leave it open. And this is the one-piece corner of the Dragon Wagon. If you wanted to take the leg off, you can. If you're gonna use it as a platen on top of the table, obviously you're probably not gonna have legs on it, so you can get to all these bolts because this is open in here. And then this is where the leg mounts to these big bosses that go up all the way to the top of the table. And you can just see how thick it is. Everything's beefy, it's all one piece, there's no welding, right? The castings look good, all one part. That's where it gets a lot of its strength from. Pretty awesome. That's the 2 different designs. One of the most often overlooked areas on a fixture table, at least in my opinion, is the leg connection. And as you can see here, I put this leg on to demonstrate where we cut that corner off, what it looks like. And this table has a 2-bolt connection right here, and obviously the Fireball has 4. But what I really want to see is the leg actual design too, because that also plays a big part in these fixture tables. And these things are expensive, so we want to see which one is a better design. Well, let's take this off and check out the leg. These things are a pain in the butt to put on without the table. Take this one off too. All right, let's take a look at the legs. It's a 2-piece construction because it's telescopic with 2 pins. Powder coated. There's some slop in here. This might be an issue later down the road. We'll find that out later. Slot bolt directions. Here's the casters. Looks like the material's about 12 gauge or something. No grease zerks on the wheels or that center 2-bolt construction right there. All right, Fireball leg, pretty substantial. We got 3/16 tubing, nice big 4-bolt flange, heavy duty. Let's flip it over. Nice big heavy duty casters, brakes, grease zerks, much thicker caster design when you look at the sides here. So if this were to hit something, this could potentially fold over. This one has bearings in it. This one does not. Overall, much beefier caster.
I quickly weighed the Siegmund leg and it was 8.35 kilograms, which is about 18 pounds. The Dragon Wagon leg was 14.15 kilograms, which is 31 pounds.
Another thing, let's do the rattle test. Kind of rattly. Fireball, no rattle. Why is there no rattle? Take a look. See these pins right here? These pins are specially made because we laser cut the tube so that the bolt can go all the way through and sandwich this tube to this back wall, removing all the slop from the telescopic tube. See how nice a fit that is? And what I want to see is that when this table is fully extended and this leg is underneath of it, how much wobble does the table have? All right, let's put them back on and we'll do the wobble test. What does this mean to you? You're probably saying, Jason, I don't care about the dump leg. Big whoop-de-doo. The table just needs to sit there. Well, that's exactly what I'm gonna show you. I've got the legs extended fully, and I've also given this the best chance for wiggle. What I mean is if you look at the way the legs are, I got 2 pins on one leg going this way, and then the other 2 leg pins are going this way. And what that means is the telescopic leg wants to pivot on the pin so that they're kind of counteracting each other. So they're kind of balancing each other out to give this table the best anti-wobble possible. This one's a little higher by 2 inches. And as you can see, 41, close to maximum height. And then this table, 38 and 3/4. Okay, let's do the wobble test. Yikes, pretty wobbly. You can see it, it's all in these joints right here. People ask me all the time about trade shows is how wobbly is the table when it's at full height? Maybe that's an issue, maybe not. I don't know, these are expensive tables. I wouldn't want mine to wobble. Well, let's try it over here on the Fireball table. Much better. Yeah, it's got a little wiggle, but that's all in the caster joint right there. We only have 1 bolt in it, but even there with that handicap, that is so good. This is what I'm talking about when you buy something. You can just like feel the quality. You're like, oh man, somebody was thinking about this. Night and day difference, pretty crazy. The next thing I'm always worried about as a designer is this connection from the table to the leg. How strong is it? And why am I worried about that? What happens if this table leg hits something? How strong is it here?
One scenario that these tables could face is a forklift backing into it, applying pressure and potentially damaging where the leg connects to the table. To simulate this, I'm going to do what I did in an earlier test and chain these legs together, applying the same force and slowly pull them to test their strength.
All right, so 1, 2, 3, 4, I declare a leg war. Let's do this. So here's the setup. I got both tables
turtled upside down and I've removed the legs. What I want to do is just pull from caster to caster. What we're looking for is this connection right here in the table. Is this connection strong? And in order to know that it's strong enough, I needed to compare it to the other table, okay? Here's how I have the table fastened. I got it fastened through bolts through the big Fireball Magnum table, all right? So really we're just isolating the leg and this connection. And this happens on both tables, and the bolts are relatively close to the same spot on each table, so it's pretty fair in that situation. Okay, we're gonna be pulling up high, and we're gonna be pulling with this chain hoist, and I'm gonna stand off to the side. We got GoPros looking at the connections so we can see if something's moving. We have a camera pointed at the load cell right here so we can see how much force we're applying. Before we get started, here's the wiggle test again, all isolated from the table. Quite a bit of movement there. I got the pins running this direction, and on the Fireball table, I got the pins also going the correct orientation. Look at the movement, or lack thereof, zero, pretty stiff. So it's gonna be an interesting comparison between the two fastening points at the table and these pin connections to see at the end of this, does this still telescope? Same with that little leg over there. We're gonna learn a lot. All right, let's rock and roll. Might need to stand over here. Ooh, this is already bending pretty bad. Whoa, what are we up to a pressure here? About 500 kilograms. We've already cracked it. There's a square how much it's leaning with 500 kilograms and 24 inches. Let's take a look at the Fireball leg. Fireball leg's looking pretty straight. It doesn't even look like it's moved. I don't know if it has moved. One of these things is not like the other. Let's just keep pulling. Watch out, it's gonna break. There she goes. All right, what do you think about that? Let's take a look. Wow, just totally pulled it right out of there. Pretty wild. It was actually pretty easy. I didn't take that much force at all, actually. Let's release this and see what we got. I'm actually surprised that the bolts didn't pull out, but the leg mount destroyed. That's really fascinating. Interesting results. Look at how that metal just cracked. That's from this being hardened. Fascinating. Really cool. Looks like the Fireball leg hasn't budged an inch. The point of these exercises is for me to really test and put this design through its paces. So what I want to do is reset up the test again, but I'm going to attach the leg over here to this table back over here and pull off of it. The goal here is to break the Dragon Wagon. I'm not trying to make this table look bad in any kind of way. I just want to compare it to this table. So let's bolt this leg back to the outside. So let's do it again. All right, round 2. Break, baby, break. Come on, Dragon Wagon, break a leg. Let's go. Dang, this one's already snapping over there. Let's go. Come on, break. Break. Nope. Dang, we're just freaking reefing that leg over. We're just bending the tube. Let's just keep going. Come on, break. Oh, okay, not gonna break. What are we holding at? Ooh, 1,200 kilograms. That's a lot of load. What's that? 2,645 pounds are on that leg right now. You can definitely see that it's pulling. A little buckle in that flange, not bad though. Whew. This one does not look very good though. I say we just keep going. Break, leg, break, come on. Ugh. Come on, leg, pop. Jeez. We're definitely buckling, check that out. Whew, it's kind of scary. 1,384 kilograms, 3,051 pounds. Take a look at that. We are finally seeing some distortion here at 3,000 pounds of side load. That's pretty impressive. And then look at this one. Here's what we got. That's kind of what I expected was gonna happen. I needed to pull up against something. Okay, so we have 3,000 pounds of tension on this. I'm gonna whack this right here. I'm gonna see what breaks. I need this to break. Here we go. 3, 2, 1. Oh, hit it, you stupid. Hit it with your purse. Break. For crying out loud. Let's hit it some more. I need a bigger hammer. Okay, here we go. It's kind of hard to swing. Oh! 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 Hell yeah, baby! That's what I'm talking about. Let's check out the breakage. Look at that. The heads of the bolts popped off. You know, cast iron gets a bad rap, but when it's designed properly, it's very strong. So when I hear people say cast iron sucks and it's just gonna break off, well, you know what? I don't think you truly understand what's going on here. Design, man, design. Look at that, that's pretty cool. Let me see if I can take those out. We'll look for any cracks. Okay, let's take a look. Not bad. That looks like nothing ever happened. What the heck? Ugh, here's the leg. Wow. I mean, that's some serious force. Pretty good. Welds are barely even pulling. This is just such a superior design. Here's the cool thing about that. You could replace the leg and go back to work. Let's take a look at the other side. Okay, the leg obviously isn't designed for this, but one of these tables is going back into production and one of them ain't. Jeez, look at that. Puckered. Impressive. Pretty dang good. Now that we saw the slow push, will these leg connections react the same if they are hit with this force suddenly, like going down a stair step? To simulate this, I need a repeatable force to impact both of these legs. So let me introduce you to my hammer. This is the rig that I use to test the Fireball hardtail vise, and it's perfect for testing my table leg design. This hammer is going to make this test repeatable, impacting the table leg with the same amount of force every time. We got our vise testing hammer right here. We have the tables bolted down to this big, thick, 2.5-inch thick plate steel right here through the center of the table. And what I want to do is swing this hammer around and impact right here. What this is going to simulate is this leg hitting that abrupt edge, something in the concrete. Hopefully we see maybe some bending with the caster. And of course, we are really trying to look at this connection right here at the table and seeing what happens. Do I know what's gonna happen? I have no idea. Couple notes, I really don't have the table optimized in location. What I mean by that is hammer's gonna be coming down at a downward angle, striking this plate right here. We're gonna see how that affects it. This table and the Dragon Wagon are going to be hit in the same location, so it really doesn't matter as long as everything's the same. I've also shrunken the leg down short. Why? Because anything up here is just kind of wasteful anyway. We're actually looking for this connection and this connection. I think this should simulate this pretty well, but the only way to find out is to swing the hammer. I only got one chance at this, so cross our fingers it works. We have GoPro set up everywhere. We got a high-speed camera set up. We got slow-speed camera set up. So we should see something pretty cool if we only get one hit and this breaks. But hopefully it goes longer than that. I want to see this design be successful. Okay, let's get this party started. Break a leg. Okay, watch out. Here we go. Hammer's coming up. How many hits is it gonna take? 3, 2, 1. Ooh. Pretty good. One hit. That actually did better than I thought it would. Definitely not straight anymore. Here she goes. Ooh. We're seeing, like we did before, that stress fracture down here at the bottom. Sheesh. It's weird how that hardened steel just wants to crack. I think this next hit is gonna do it in. So that's what, 2? After the first one, it was pretty bent. Keep going. Let's crank this baby up. Ooh. Started to split it, that whole plate off the back wall over here. Wow. Caster still turns. Oof. Yikes. Still fairly straight.
No, maybe not. Not straight. Took some destruction. I want to see it hit, but I think it's gonna miss it.
Next hit. 3, 2, 1.
Okay, I gotta see if the Dragon Wagon can do better than that with 4 hits. What I find interesting though, even after the first hit, this was kind of already bent. You really don't want the table to bend or break. Kind of want all the damage to go into the leg so we can just fix it. Pretty interesting results. Cool.
All right, next up, the Dragon Wagon.
Here we go, first hit. It's gotta get past the first one first. Damn, that was solid. Second hammer blow. 3, 2, 1. Wow, look at the flange bend. Look at that. Man, that hammer hits hard. Dang. That's what I want to see. Man, if you hit something that hard, that we have 4 or 5 more hits before these 2 pop off. Those are coming off here. Hit number 3. Yeah. Wow, that was funky. Let's go. Oh. The leg took all the damage, but the casting is fine. The cool thing is these bolts and legs are replaceable. That's pretty neat.
After putting this table through the strength and durability challenges, can it truly claim to be the best in these categories? Well, I don't think any table can claim this. There are so many factors that make a table the strongest and most durable, and no table is going to be the best at every single challenge. There are trade-offs to design choices. A table might be incredibly tough, but sacrifices flatness and accuracy. Another may excel in precision and flatness, but can't handle heavy impact without sustaining scratches or dents. What do you guys think? Join me on the Fireball forum so we can discuss this even further. Thank you guys for watching, and I'll see you in the next video.